Alright, this is section 1, functions and domain versus range. A lot of function notation as well as just a study in domain versus range. So, a few things just right off the bat. What is domain? Domain is the set of inputs, which is your x values. Anytime you have a function, you're inputting something into it and you're getting back out that range, that outputs, which is your y values. The other way that we can look at this besides input and output, and it's just like any function. If you put bread into a toaster, you get toast back out of it. You input something and then you get something out of it. The other way you can think about this is independent and dependent. What is it dependent on? Well, what I get out of the toaster is dependent on what I put into it. So therefore, the range is dependent variable and domain is the independent variable. Because the domain is what I put into a function, therefore it's independent. The range is just whatever I get out of that function. A function is a relationship between the domain and the range where each input in the domain corresponds to exactly one output in the range. And we're going to talk a lot more about what that looks like and about what is a function and what is not a function here. So, again, functions are domain goes into the function and then range comes back out of that function. The other way you can remember this is a mnemonic device, Dr. ID, XY, and then Dr. and ID, and then IO. IO stands for input and output. The D there under the X stands for domain. The R over there with the Y stands for range. The I is independent, and the D is dependent. And this little mnemonic device is just a good way if you're struggling to remember what is the input and what is the output in terms of X and Y, which one goes with which. So remembering that the X and the Y, the X goes with the independent, the domain, and the independent variable, and the Y goes with output, range, and the dependent variable. Now, what does that look like when it comes to a function? Remember I said we're going to do tons with function notation. And so it's really important to understand that this f of n right here is a function. And whatever you put into the function in these parentheses right here is what goes into the function over here. So f of n, and that's why it's read f of n equals n plus 5. If that's f of 3, well then that becomes 3 plus 5. And if that's f of x, that becomes x plus 5. And if it's f of elephant, it becomes elephant plus 5. And whatever goes into the function goes in there. And then whatever you get when you actually do this is the function over here. And whatever comes out of that is your output. So there's that idea of input and output again. Another way you can think about this when we're trying to figure out is it or is it not a function is with like birthdays. Everybody can only have one birthday. So every single person is the input. When you put a person into the function, you have a birthday. But no one can have 2 birthdays. That's illegal. So when I look at this function here, I see that every input, right, is the x values, 0, 1, 3, 4. And my outputs are all the y values, 1, 2, 1, negative 1. Now, it doesn't matter if the y's repeat. All that matters are does each x value have exactly one output. So when I look at this, I look at all of my zeros. Well, here's my 0, right? There's only one output. 1 has only one output. 3 has only one output. And 4 has only one output. If there was some craziness where I could add something to this real quick and I had like 3, 2, right? Well now, 3 has come up twice. There's this time where 3 comes up and then I input 3 again into this function, and the first time it kicks out a 1 and the second time it kicks out a 2. That makes it not a function. But the way it previously was, it would be fine. Let's take a look at this one. How about this set of numbers here? Function, not a function? Well, I take a look at each input. They have only one output, therefore this is a function. Next one here. I look at all my x values. See all these? None of them repeat. Therefore, this is a function. There's not even a chance for it not to be a function. So yes, that is a function. How about this one? Oh, so great. You're right. That's no, it's not a function. To where negative 6 shows up 2 times. And the first time negative 6 is negative 4. Second time negative 6 is negative 8. Therefore, no, this is not a function. And then one more right here. Yep, you're catching on. No, it is not a function. Now let's talk about function notation. Here is a function, f of x equals 4x squared minus square root of negative 6x, and they want us to figure out f of negative 4. So if I'm going to do f of negative 4, what is my input? Negative 4. So this becomes, everywhere where there was an x becomes negative 4. So 4 times x squared becomes 4 times negative 4 squared, minus the square root of negative 6 times negative 4. And that becomes, if I remember my order of operations, I have to do parentheses and exponents first, so I got to do this first. So negative 4 squared is 16. Then I also got to handle what's inside here, which would make that the square root of 24. So f of negative 4 then becomes 64 minus square root of 24, which I can simplify down to be, if I use the cake method with a little 24, take some 2's out, and I end up with a pair of 2's there, so they get to come out. 2 and the 3 stay inside, which becomes 6. So 64 minus 2 square root of 6 is the best that we can do in terms of this function. So you'll notice I wrote f of negative 4 all the way down because that tells me a lot. That says the function, when I input negative 4, I get 64 minus 2 square root of x out. So it's a lot more than just writing an answer and boxing in here. I would box in the entire thing because that f of negative 4 tells me something about the problem. Okay? Let's look at a little more complicated one. How about this? G of x equals x squared minus 4 over 4x. And they want to find g of n minus 3. So we want to do g of n minus 3. So now my input is an expression. Everywhere that there used to be x is going to be replaced with n minus 3. So that becomes n minus 3 squared minus 4 over 4 times n minus 3. Now I need to simplify. I need to simplify exponents, so I got this n minus 3 squared. And how do I simplify that? Well, n minus 3 squared is the same as n minus 3 times n minus 3, which means I need to FOIL. First, n squared, outside, minus 3n, inside, minus 3n, and last, positive 9. So this becomes up top, n squared minus 6n plus 9 minus 4, all over 4 times n minus 3. Combine like terms up top, and I have n squared minus 6n plus 5, all over 4 times n minus 3. Again, this is g of n minus 3. Now, that's a perfectly fine place to stop, but I'm going to go a little bit further because I got a sneaky suspicion that the top can be factored. And so I'm going to go backwards in FOIL and think of what the first and the last would be and do factoring and break n squared down into n times n. And then I look at the 5 and I think, what multiplies together to be 5? Well, 5 times 1. And then I need that to add up to be a negative 6, which is going to be a negative 5 and a negative 1. So now I have n minus 5 times n minus 1 over 4 times n minus 3. Nothing simplifies more, but that is extremely helpful when we start graphing these and sketching graphs of them, because I can tell my x-intercepts, I can tell my vertical asymptotes, I can tell all sorts of important information from this form that I couldn't tell from this form. So work to be able to simplify all the way down. Okay? Now, on the next video I'm going to do this really fun calculus problem, but I'm going to go ahead and stop there on this one and give you, here's the homework. Just make sure you have that down So that's due on Friday. So I'll see you guys later.